Okay, so let's do geometric sequences in series. Some will be finite, some will be infinite. Let's do an equation for this sequence. We have 0.5, 2, 8, and 32. We're going to write an equation for it. We have a general equation, which is a sub n equal to a sub 1 times r to the n minus 1. R is our ratio, where we had arithmetic sequences that had a common difference between every single term. There is a ratio between our first term and our second term, and then the second and third and fourth, and so on. So if we look at the second term over the first, what is the ratio between those two? So if we looked at 2 over the half right here and reduced that, we would get a 4. So that's our ratio. And if we checked and did 8 over 2, well, yes, that reduces to 4. And then 32 over 8, also 4. So our first term is, of course, 0.5. And then we don't know n, how many terms we have, because you see, of course, the ellipse, which means, hey, it goes on. So this is our equation. A sub n equals 1/2, or 0.5, times 4, our ratio, to the n minus 1. That's our equation. Let's do another equation, I believe, for the sequence that has a fourth term of 5 and a ratio of 6. So we're going to write an equation, but given different information. So I think we need to go find our first term. We have a different term. So let's put that stuff in. We've got a sub n, some a sub n. We don't have a sub 1. We've got this ratio of 6 to the 4 minus 1. So let's reduce that. We have 6 to the third power equal to 5 to find a sub 1. So now we have 5 is equal to 216 equal to a sub 1. So that gives us this crazy fraction, but it's 5 over 216. That gives us a sub 1. So what does that leave us with? That leaves us with this. A sub n is equal to 5 over 216 times our ratio of 6, which we were already given, to the n minus 1. Now we're going to find geometric means of a sequence. We had done arithmetic means before, which just meant we were looking for missing terms. So we have a first term, we have a last term. So we're going to go back to this equation, a sub n equal to a sub 1 times r n minus 1. So that means we have an nth term, we have a first term. We need to find the ratio. So let's use these first terms, and we are missing the second, third, fourth. We have a fifth term. So let's fill in that information. So we have 1,250 equal to 2, our first term. We do not know the ratio, so let's do 5 minus 1. So we have r to the fourth equal to 625. So to get rid of this fourth power, we could do several things. Let's think of it as getting rid of the fourth power as if we raise all of this to a 1/4, using those power rules, 1/4 times a 4 would get us to a single r. So we will do that 1/4 power to 625. So here we go. We've got 625 to the 1/4 power equal to our single r. Now, if we do that, you've got some fantastic handy dandy calculators. You could also think of, what do I do 4 times to get 625? And that would be 5. This should say a positive and negative 5. A little mistake there. Why do I have a positive and negative 5? Well, since I have an even power here, that means I have 2 possibilities. I have a negative times a negative, which would be positive, times a negative, which would also be positive. So you give me this positive 625, and then of course positive 5, positive 5, positive 5, positive 5, positive 5 gives me 625. So I have negative 5 and positive 5 that works to give me positive 625. So my ratio could be these two numbers, positive 5 and negative 5. So let's see what that works out to find those geometric means. So if I multiply 2, my first term, by the ratio of positive or negative 5, here's what I end up getting. So the next geometric means would be 10 or negative 10. The next one would be 50 on both instances. Then multiplying by the positive or negative 5, I get 250, or I get negative 250. Okay. I'm going to decide if a series will be convergent or divergent. Some vocabulary. Convergent means I have a sum that does not exist. So these are infinite series. This is not definite number of terms for a geometric series. So if we're talking about infinite, they go on and on and on. An indefinite number of geometric sequence numbers that have a common ratio. So if they're convergent, that means they're going to approach a value if I continue to add up all these numbers that are related to each other. Or I might have an infinite series that is divergent. That means the sum does not exist. And there's a reason why that happens. It's because of the ratios that they have. If I look at this series, they're convergent because their ratio is less than, really it's the absolute value, because I could have a negative 2/3. Because the ratio is a fraction, which comes out to the absolute value less than 1. So if I do my second term over my first, I have 36 over 54. It reduces down to a fraction whose absolute value is less than 1. If I look at this other series and I compare my second term over my first, I have 1/8 over 1/16. We need to remember our fraction rules from grade school. When I divide one fraction by another, I end up multiplying by its reciprocal, so 16 over 1, and that gives me a 2. This ratio, its absolute value is larger than 1. If I have a ratio whose absolute value is larger than 1, I'm going to get a divergent series. That means that this series is continuing to grow. I have numbers that are growing and growing and growing. And if you can remember, we have graphed, and you have done in science, you have exponential growth. So these numbers are growing in value, and they're continuing to grow, and the numbers are getting larger. And as you add larger and larger numbers, your sum is going to get larger and larger. This one is a decay. And as you continue to add, you'll be approaching a value that just does not grow much anymore. So it's going to approach a specific value. Here's another way they could give us a series. So this is a shorthand notation for giving us a series like we saw a moment ago. So I could give you this series, but I could give it to you in this sort of notation. It's called summation notation. And that would be really nice if I did that. So what it does is it uses really this format, this equation here, and tells you to add them all up. That's what this Greek letter, this means sigma. And it's telling you to add all the numbers that behave with this equation. And it means the summation. So do we remember where r is in this equation? So it's really just this part of the equation right here. So where's r? R is right there. So if that r is bigger than 1, which 4 is, then this one is divergent. So this does not have a sum that exists. So let's look at another one. How about this? Does this have a sum that exists? Is it convergent or divergent? It is convergent. We have an equation for this. So because you have a cool button on your calculator, if we had a finite series and this did not have infinity up here, because your calculator will say, can't do it. So we have actually a summation equation that we can do. So we can take this and go, oh, I know what to do over here, because I know my ratio, which will go down here, and I know my first term, which will go on the top. Because this is convergent, I can actually do this. So I can do 3 over 1 minus 4 over 5, and I will get 15. Okay, so let's find the sum of an infinite geometric series when they give it to you as a series rather than a summation. Here we've got 2/3 plus 6 over 15 plus 18 over 15 and so on. Obviously it's infinite. We have that ellipse. It means it continues on. So let's check, can we do this? Let's look at the ratio. So 16 over 15 over 2/3. So 16 over 15 times 3 over 2. We get 3/5. That's a ratio that we can do. It converges. Its absolute value is less than 1. So we can use our summation. So here we go over to our summation is a sub 1, our first term, over 1 minus our ratio. And when we do this, we get 5/3. So we can actually find the summation. Let's find the sum of this geometric series. Let's check this out. If we check this ratio and we do our second term over our first term, 9/6. Think about that. What would a ratio of 9/6 be? Is that a fraction that will be less than 1? No, it's not. 9/6. I have a student that says that's a Dolly Parton fraction, bigger on the top than on the bottom. So that is divergent. We cannot find that summation. One more. Find the sum of this infinite geometric series. So if we check this ratio, -2/4 sounds like a fraction we can do, and we can reduce it. That'll be a -1/2. We can do this summation. So here's our a⁻1, our first term, over 1 minus -1/2. Change our signs. If we reduce this, we get 8/3.